pressed it. 1, 2, 3, 4, 5. It's recording.
Okay. So I want to do a review of what I did yesterday. So, what did I do yesterday?
We had union sets, and we had unions and intersections, and we had complements, and we had universals. Was that right, or what?
Well, I did talk about I did say the word universe at one point.
There was the big C. What was that?
That was complement.
Oh, what was the little c?
Oh, the big. Oh, you mean the subset?
Oh, okay.
And then the little c was the complement.
Oh, okay.
And we also had the element symbol and the not element symbol, the set brackets, which is that, and then the union, and then the intersection, and then the complement was a little c, right? Is that starting to all rush back into memory?
Put the little c by the word complements. You're going to totally confuse me.
Okay.
All right, yeah, we're ready to go.
Well, no.
No.
That was just, I'm just trying to get the machinery going inside the head. Okay. So, but I want to go over the definitions and stuff too. So, if we had A union B, and we draw the picture A and B, then what is A union B? What would I fill in?
Oh, you mean like the common numbers? I'd have to know what was in A and what was in B.
But I mean, yeah, but if I just say this is some set and this is some set, and I'm shading in whatever A union B represents, what would I shade in?
The middle, the intersected part.
But it's union, not intersection.
I don't know.
Because it's like a U, right?
I don't know.
So for the union, I take the union of both sets A and B, so I end up with everything, right?
Oh. I'm bad.
And A intersection B. A, B. What would I fill in for A intersection B?
That, where it intersects.
There?
So if A was 1, 2, 3, and B was 2, 3, 4, then it would be 2 and 3.
That's correct, yes. Okay. So that's what union and intersection mean.
Okay, so if in union A was 1, 2, 3, 4, and in B it was 3, 4, 5, 6, it would be all those numbers.
Yeah, it would be 1 through 6, right? Okay.
See how smart I am?
I'm very impressed. And so if we have a picture, so if this set is A, what is A complement going to be? What would I shade in?
I don't know.
Well, right, so I have to also draw a box here, which represents everything that could possibly be in the set, and I would just shade in the whole thing, right? Except for A. A complement is everything outside of A. So I would say this box is U. It's the universe, everything that could go in sets.
But, if you just... I'm confused. So, if A is say even numbers, and that's the set, what's the complement?
So it depends on what the universe is. So if we say that all whole numbers, we're only considering whole numbers, like 1 through infinity, and -1 through -infinity, and 0, then in that case we would end up with just all odd numbers, right? If A were if A were 0, 2, 4, 6, dot, 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 together with -2, -4, -6, dot, 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 right?
Yeah, I have a question. What if 0 weren't in there?
Well, then 0 would be in the complement.
Oh, okay.
Then a complement would let me.
So 0 is both even and odd then.
No, 0 is even.
Oh. Because you go 0, 1, 2.
Yeah, because that's how we define even numbers, is that they're 2 times some number, and 2 times 0 is 0, so it's even.
Oh.
So a complement is going to equal 1, 3, 5, dot, 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 union -1, -3, -5, dot, 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 and why don't we also just put it in 0? Because it's not in here. Right? Does that make sense?
Mm-hmm.
Okay. So now I have a good idea of what a complement is, and the fact that we can define a universe so that the complement makes sense. Okay. And I think one thing that I didn't talk about yesterday is that we could have an empty set, which just doesn't have anything in it. Which we often is written like that, called the null set. Right, so if we took the complement of the universe, that would equal nothing.
How scary.
That's like, yeah. Right, so does that make sense? We have a null set and we have a universe, and they're sort of the opposite of each other.
It's scary that it makes sense.
Okay.
It was a Zen moment.
Mm-hmm.
Okay.
And we also have subsets. In fact, we could say that the null set is a subset of the universe, because every element in the null set is also in the universe, because there's no elements in there. So this is referred to as something that's vacuously true, that if an element were in here, then it would also be in here because there are no elements. It's a sort of a mind-bending thing. But in fact, it's true that the null set is a subset of the universe.
So, do a subset of something else, like.
No.
No.
I think.
So do a subset of like the even numbers thing.
Okay. So yeah, if I look at 2, 4, 6, this finite set, that is contained in the set of all positive even numbers. Right? This is a subset of this, right? So I hope that's a good example of a subset.
So if your set is just 2, 4, 6, nothing more.
Yes.
But a subset could be all even numbers then.
Right. I could say that all even numbers are a subset of all numbers of all positive numbers. Right. I could say, just look at 2, 4, 6, 8, dot, dot, dot.
Mm-hmm.
I could say that's a subset of 1, 2, 3. These are both infinite sets, right?
Oh.
But this one is a subset of this one because every element in here is also contained in here. If I take any arbitrary element of here, I can find it over in here. Would you say that's correct?
I guess.
Because, I mean, if I take, say, the number 1000, that's an even number. 1000 is also going to be over here, because this contains all positive numbers. So in particular, it's going to contain all the even ones. So that means that this is a subset of this. And I could also say that something, if I take this any set, it's going to be a subset of itself, of the same set. Because these two are equal, so that means that this is going to be a subset of this one. It's just sort of a trivially true thing. That if I take an element in here, it's also going to be in here, so this is a subset of this, and this is also a subset of this.
What if your set was a triangle? What would the subset be?
Well, it would just contain one thing, and that was a triangle.
Mm-hmm.
Like this.
Mm-hmm.
Well, it only contains one element, so this only has two subsets. The set of all subsets would be the empty set and the entire set itself. These are the two subsets of this set containing one element.
Oh.
Does that make sense?
What if it had a triangle and a square?
Okay, then we would have more subsets.
So you couldn't say a subset are geometric shapes then.
Well, sure. I mean, you could have the set of all geometric shapes, and then look at the subsets of that. But for the moment, let's just look at this what you propose here: triangle, square,
Mm-hmm.
right? And let's look at all the subsets of this set containing two elements. We have the empty set as before. The set containing no elements. That's one subset. We also have these sets containing only a single element. And then finally, we have the set itself. So we have four subsets altogether. This is all subsets of this set.
So if it were a complement, then maybe it would be all geometric shapes. That would be the universal.
Right, we could define the universe to be all geometric shapes and define geometric shapes in some way.
Mm-hmm.
And then we could talk about subsets. This is a very mathematical way to think about approaching of this. One thing that I have not defined that you sort of have been led to by these questions is the power set. So if I look at the power set.
Whoa, the power set.
Of this. This is defined as the set of all subsets of this set. So in fact that's equal to this if I just draw brackets around it. Because we can have a set that contains sets. So the power set of this set is the set of all subsets, which looks like that.
Okay.
And right, this is kind of interesting when you apply it to like infinite sets and stuff. But I won't go into that.
No, don't go into infinite sets. They're just as disturbing as the null.
Right, the guy who sort of invented this theory, I think he may have gone a little bit crazy at some of the stuff he discovered. Cantor.
What was his first name?
Georg, I think. But yeah, one thing I think the thing that disturbed him most was that he discovered that maybe it wasn't what disturbed him most, but I recall reading that it disturbed him that the fact that the number of whole numbers is the same as the number of rational numbers. So if you look at say 3/4 or whatever, like all rational numbers, two whole numbers in a ratio, it's the same as the number of just whole numbers. And the reason this is kind of disturbing is if you look at an interval, 0, 1, like all the numbers between 0 and 1, the rational numbers are dense in this interval, and if you take any point, you can find a rational number that's arbitrarily close to that. So if you fill in all the rational numbers, it'll basically fill in this whole thing. So there's a lot. But at the same time, the number of rational numbers is not that many because it's the same as the number of whole numbers. And so to a mathematician at the time, I think this was just a really disturbing thing. I don't think I've explained it very well, but this is kind of more advanced stuff. So I shouldn't go into that too much.
Notice that I'm silent.
Yes, yeah, I didn't resist the temptation to start talking about that, but yeah, it's definitely off topic. So you have power set, union, intersection, right? Union, intersection, element of, subset.
Do they call them rational numbers because you have to? They're
Because-
related to the.
Because they're in a ratio.
Yeah. Oh, okay.
Yeah, I think that I think that's where the word rational comes from. Is the ratio, and
Cool.
so yeah, it's not like we're saying they're rational as in they're logical. That's more of that's the origin. That's why we think of rational as meaning logical, because the rational numbers are considered like more sensible or something.
I agree.
As opposed to real numbers. But I'm not going to talk about that. I'm resisting the temptation. Okay, so that was just a review. I also want to talk about the identities. So,
Are we gonna get to proofs?
yeah,
Yay!
I thought you didn't want to get to proofs, but this is where we're leading to. Shut up.
Well, it's anticipation, Alex.
Okay. Okay, so yeah, but I'm going to prove some of these identities is the thing. So we have De Morgan's laws. If we look at A union B, and we look at everything that's outside there, that's the same as A complement intersection B complement. Right?
Alex,
What?
you've got to give me about 10 minutes to figure this out.
So what we do is we say A union B, and we take the complement of this union set. All that we do is we take the complement of A, the complement of union, and the complement of B, right? So we flip the union around and we take the complement of both of these. Do you remember that? So this sort of makes, so mechanically it's sort of easy to do this as an operation, is we just distribute the complement inside to all three parts. If we just, like, this is, like, if we just define union complement equal intersection, like, this doesn't make sense, it's just to make it easier to do, right? And if we look at A intersection B complement, that's equal to A complement union B complement. So we do the same thing, we just negate all three parts.
You want to know how stupid I feel right now? Okay. And this is all logical, right?
Well, I'm not talking about logic. I'm just presenting these as true things. There's no reason to believe that it's actually true at this point. I'm just stating it.
Oh, okay.
If you take the union of these two and you complement them, then you can just complement the individual parts, and it will work. It's just like we would like this to be true, because it's sort of easy to do it, and we don't like this complement on the outside. We would rather deal with individual parts. A complement intersection B complement. We don't have like a parentheses in a complement, which is just nicer. And so just having this identity is useful.
Okay. Why don't you pick her up and say hello? Let her say hello to
Okay.
poor Ivy.
It's okay. Come here.
There we go. There's Ivy.
Hey. Okay. You gonna shut up, cat? All right. There you go.
Come here, Ivy. You can watch.
Okay. And we also had some other things. So if we take A union A, it's going to equal A. And if we take A intersection A, it's also going to equal A. So these are identities. So there's a binary operation with sets where if we take two of them and union them together, we'll get the same one. We'll get the first one back. Anyway, this. Okay, so we have A union A equals A intersection A equal A. We also have A complement equal to A. So these three different ways that we can get A back again. And we also have the distributive laws. Which are A union B intersection C equal to A union B intersection A union C. And this is similar to if we were to take A times B plus C equal A times B plus A times C, except we replaced times with union and plus with intersection. But it's easy to remember that how this works that way. And we also have the other distributive law, which is A intersection B union C equal A intersection B union A intersection C. Okay. So that makes perfect, complete sense?
Absolutely.
Mm-hmm.
No, prove it.
I will prove the distributive laws later. But I wanted to start with an easier proof. I wanted to start with how do we prove that generally that A is a subset of B. And the way that we could write this logically would be that X, an element of A, implies X, an element of B. So this is a logical implication that is equivalent to saying A is a subset of B, is that given any element X in A, that should imply that X is also in B. And if that is not true, then A is not a subset of B. But this is, thinking of it this way is a good way to prove it. And the way that it would go is as follows. We have a proof. And we would say, suppose X is an element of A. And that's this first part here. We suppose X is an element of A. We suppose this statement is true, and we try and prove that this statement is true, so that this implication is true. So down here we would say, therefore, X is an element of B. And that would be the proof. And in the middle here we do some logical argument to show that X is an element of B, and that's what's missing here.
So what is that square down there? That means proof?
Yes, that means that it has been proven. That's one way of writing it. We just have to have we have to follow some convention to show that we've reached the end of the proof. Okay. So let me give an example of this. So we're going to prove that A union A is a subset of A. Right? This is how we prove it. First we suppose X is an element of A union A. And then we're going to show that X is also an element of A. We take this arbitrary element that's in A union A and show that it's in A as well. So we say therefore X is an element of A, or X is an element of A, because we have the union corresponds roughly to the word or corresponds exactly to the logical word or. That X being an element of A union A is equivalent to saying X is an element of A or X is an element of A. It's in this or it's in this. And so then we have, therefore, X is an element of A, which is this set. So finally we have A union A is a subset of A. We've proven the logical implication X an element of A union A implies X an element of A, which is the same as proving this by definition.
So someone actually thought this up.
Yes, essentially the Greeks did a long time ago.
Oh.
the whole idea that you can prove things with math. We're sort of skipping the foundations of it, but I think this is still useful. Right, so this is how we prove that A union A is a subset of A. And we can also prove that A is a subset of A union A. So again, we're trying to prove the implication X an element of A implies X an element of A union A. So we suppose X an element of A, we suppose that this statement is true, we try and show that this statement is true as a result so that this implication is true. So therefore, X an element of A or X an element of A, therefore, again, this or, the logical or, is the same as taking a union. So AX is an element of A union A. Therefore, A is a subset of A union A. That's what we're trying to prove. Does this make sense?
Yes.
Okay. Could you prove this yourself, do you think?
No. I forget one of the therefores probably.
Okay, so we're trying
I'm just going to write the little square, you know. It's proven.
Okay. So now I'm going to prove that A union A is equal to A, and this is not this is sort of you're going to have to give it a little bit of convincing for this. Okay. So the first part is that A union A is a subset of A. We've already proven that's true. And we've also proven that A is a subset of A union A. And therefore, A union A is equal to A. And that's the whole proof. So what we need for this to be true is that A is subset of B and B subset of A implies A equals B. So we need this implication to be true in order for this proof to work, right? That I'm just assuming that if this is a subset of this and this is a subset of this, then those two must be equal, right? That makes sense, doesn't it? Like it makes intuitive sense.
Yeah.
So we just assume that this is true. That if we can show that, then this is true. And this is actually something that we just take as an axiom. We take it as being something that's self-evident so that we can proceed and do stuff. And that's what we do in axiomatic mathematics, the sort of all pure mathematics, all rigorous mathematics. We work from axioms and we go from there. We make some really basic assumptions and see what we can do with those.
What does pure mathematics mean?
That's a good question.
That it's meaningless?
Well, it means that your intent is not, you don't necessarily have any particular application in mind. People studied prime numbers and stuff for a long time without thinking that there was any application of it. It turned out there is applications to cryptography and stuff like that, but they just did it for the sake of doing it largely, and for broadening the knowledge of how stuff works in these areas of pure mathematics. So there may be applications, but that is not that's not the initial motivation necessarily. I think that nowadays the divide between pure and applied mathematics can be a bit more arbitrary than that. Like, it may just be more what field you're interested in rather than whether or not you really care about applications. Because someone could be working in heavy differential equation stuff but not necessarily have any application in mind. It could be really theory-based stuff, but they may be considered applied regardless. Maybe they wouldn't be. I'm not actually completely sure on that.
So where do we go from here? Are we done?
Well, I thought I would. That seems like a really easy proof.
So you do a harder one?
Yeah. So like you wanted to see me prove the distributive laws, right? I could do those.
Oh no.
Why don't I just prove one of those to end with?
Okay.
Let's prove A intersection B union C is a subset of A intersection B union A intersection C. Right? Let's prove this. And again, the first step is just suppose that we take something in here. Suppose X is an element of A intersection B union C.
I'm feeling anxious. Okay, keep going.
This isn't too tough. This isn't too bad. So, right, so what we do is we just think of all the possible things this could mean. What does this mean? This means X is in A and it's either in B or C or both. Right, so then X is in A and X is in B or X is in C. Right? So we just rewrite that using words and logic. X is in A and it's in B or C. So what we could do is split this into cases. Suppose first of all X is in A and it's in B. 1. Case 1. X is in A and X is in B. Right? This is one possible universe. In that case, X is an element of A intersection B. Right? So in that case, we're in A intersection B here. So therefore, we're going to be in A intersection B or A intersection C. So we are in this. In that case, we are in this set here on the right. Would you agree?
Mm-hmm.
So therefore, I'll use the 3 dots to mean therefore.
Yay!
Therefore, X is an element of A intersection B union A intersection C. That's what happens in this case. But it could be it's possible that in another case, for other choices of X, that it may not be true. So we need to consider all possibilities. Case 2 is that X is an element of A and X is an element of C. Right? We have these two cases, X is an element of A and it's in B or C. So in the second case, it's going to be in A and C. Right? So then, therefore, then, X is an element of A intersection C, which is this one. So that means that we're in this set again. So X is an element of A intersection B union A intersection C. Right? Would you agree with me to this point?
Yeah, I would.
In cases 1 and 2, in both of these cases, if we take X in here, it ends up that X is in here as well. So that proves it. I would write out what we proved, but we ran out of space here. But this, are you convinced by that argument?
Yes.
Okay, and so that's half of it. The other half would be to show that this is contained in this. But I think that I won't do that because I think that it's clear that we sort of get the idea of how these proofs go. So maybe we'll stop there.
Thank you very much.
Do you have any questions or comments?
This is like mental yoga. It's like I'm starting to float, Alex. All right, it's over.
That may have been what I put in your coffee.